All right, greetings, y'all. Hope you guys are doing all right. I'll be reviewing. Ooh, I'll be reviewing 2D motion, aka projectile motion, as well as vectors, and I'll be going over numbers 2 and 3 the from homework 4, I believe. Okay, so let's start. So projectile motion, typically, you'll see a lot of these. You'll have some object that's going in this direction. You'll see a path that goes like this, or you'll have an object that goes in this direction, and the path goes like this. In in both cases, they are moving in 2 dimensions, either up and down, or left and right, one or the other. This is different from what you have experienced in the past, because in the past, you've had objects that move left and right only, or up and down only. Now we have 2 dimensions. This is moving in 2 dimensions. Okay, so um, with 2D motions, we'll be dealing with vectors which are a magnitude with a direction. And in this case, the direction will say, say this is the vector. This magnitude and this direction uh, gives you some context, some additional information about this vector. And when you're approaching problems like this, I strongly advise, actually, you have to break it down into 2 components. Being this is the vector, this is the vector's x component, call it v of x, and this is the vector's y component, v of y. And the reason you would do this is typically in these problems you'll have something that affects one thing or the other. And if you can break it down into one dimension or the other, it's a lot easier to process. For example, if you have a ball that's like this, let me just draw a regular ball. Ball is traveling like this. The arrow depicts its velocity. But how do you use this information? Honestly, if I were to just see this and I didn't know anything else, I would have no idea. But because we've gone through 1D motion in the past, um, we can approach this from this angle. This ball at every given point, at least assume, this ball at any given point, because of its trajectory, we can assume that it's being affected by gravity. And gravity pulls it downwards, which is causing it to have this motion. Um, so if you break it down into its components, you'll have this Vx, Vy, in this case, Vx, no Vy, Vx, and negative Vy. Um, Vx in every given case is constant because gravity does not affect the horizontal component of this ball, of this item. However, it does affect the vertical component, which is why Vy goes from positive to 0 and then to negative. Is yeah, yeah, you'll see that a lot. And lastly, for the magnitude, given you have a vector, right? You have a vector and you have its horizontal, Vx, Vy, horizontal and vertical components only. What is the magnitude of this vector? Um, Remember, a vector has both a magnitude and a direction. And you have these two. What is the magnitude of this vector? This magnitude is equal to the square root of Vx squared plus Vy squared. And the reason being, this is just a rearranged version of the Pythagorean theorem. You have the one leg, another leg, one leg squared plus another leg squared is equal to the hypotenuse squared, which in this case is Vx squared plus Vy squared is equal to V squared. And if we square root both sides, we'll get the square root of Vx squared plus Vy squared is equal to V, at least the magnitude of V. I say magnitude because there is no that this there's no given there's no information that is gained about the direction with this formula. You only have magnitude, magnitude, which then results in another magnitude. Um, okay. Lastly, I will be going on about vectors, which, as I said before, have a direction, have a magnitude and a direction. Um, you won't need to do this in class, at least on the exam, because she requires you to bring a protractor so you don't have to calculate angles because you guys did not go over vectors. But in case you wanted to know about vectors, and because most of these problems require that you know about how to calculate angles um, of vectors, I will teach you the following. So given you have this, as I said before, every vector, at least in 2D motion, has its components. Every vector, every vector has its components. In 2D motion, they have two components. In this case, it's going to be Vx and Vy. Now, given you have this information, could you acquire the angle? And yes, you can. How you would do that, if you remembered trigonometry, then that's how you would go about it. You would take how you would do this is the opposite over the adjacent, which is the information we have here, which is equal to Vx over Vy. This is all equal to tangent of this angle. Now, this is something you learn in pre-calculus. Um, um, so to acquire this angle, you would need to take the inverse tangent of everything. So the inverse tangent of tangent is just going to be one of tangent theta is going to just be equal to the angle. This angle is equal to because we're taking the inverse tangent of both sides, inverse tangent of this side, inverse tangent of this side. Inverse tangent of theta is just equal to theta. Inverse tangent of Vx over Vy is that, Vx over Vy, which is equal to the inverse tangent of the opposite over the hypotenuse. And that's how you get the angle. And hopefully you remember enough pre-calculus to know that if you get this angle, sometimes it won't give you this angle. Sometimes you'll get these components and you'll be over here and over here. You'll get this angle, which is this amount, but the value that they want to get is this amount. They want to get this amount rather than this amount. And hopefully you know how to do that. Otherwise, if you want to learn about this, if it's necessary in the future, you need to learn how to you need to relearn some trigs so you're able to calculate these angles of these vectors. Moving on to question number one, question number two, I should say. Okay, a ball is thrown horizontally from the top of a 52.5-meter building, lands 116.3 meters from the base of the building. Ignore air resistance. How long in seconds is the ball in the air? That's going to be the first problem, part of this problem. So when approaching these problems, I like to draw out what I am working with. Ball is thrown horizontally from the top of a building. Draw the building. I'll draw the ball. And I'll draw that it's being thrown horizontally from the top of the building. The building is this tall, 2.5 meters, and this ball lands 116.3 meters away from the base of the building, which is right here. How long is the ball in the air? Okay, let's see. How can we get that? Okay, okay. As I said, every velocity has two components, the x and the y. Let's see which one we could use to possibly get how long the ball will be in the air for. And I'll tell you right now, um, you would use the vertical component. And you might be wondering why. The reason why is because regardless if you have a ball that's still or you have a ball that's being thrown horizontally, like in the problem, at any given point in time, as long as both of them started off with no vertical velocity or the same vertical velocity, they will be in the same position at any given time. They will both hit the ground at the same time. So let's treat this ball because it's vertical, so we'll be using its vertical component to determine how long it takes for it to hit the ground. So let's start off with drawing our formulas, writing our formulas down. B final squared is equal to B initial squared plus 2 acceleration times time. B final is equal to B initial plus acceleration times time. And D is equal to DI plus acceleration times time plus 1/2. Oh, no, that's incorrect. Times velocity times time. Velocity initial times time plus 1/2 acceleration times time squared. Okay, so we need to figure out how long it will take this ball to fall to the ground with its given height and its given initial vertical velocity. What is its initial vertical velocity? If the ball is thrown horizontally, it has no initial vertical velocity. Um, Vertical being up and down. It does have a horizontal velocity as on here because it's thrown horizontally, but it's not moving vertically initially. So its initial velocity in the y direction, its initial y velocity is going to be 0. The height it is above the ground is going to be 52.5 meters. Let's see. Its acceleration that's affecting the ball is negative 9.8 meters per second squared. Any other information we have? That might be it. Might be it. Its final velocity is unknown. So let's underline what we have. We have initial velocity, we have acceleration, we don't have the time. It's the ground. We have initial velocity, we have acceleration. Of the time. The distance is above the ground. We have its initial velocity. We don't have the time. Acceleration, but we don't have the time. This is not t. I wrote this problem. I wrote this formula wrong. Apologies. AD to acceleration times distance. and we do have the distance in which it will fall. Um, why isn't it this distance? Because if you looked at the other video that I posted, um, the Saturday SI session video, I went over what each formula means and what the components of each formula mean. So, for the sake of this, just in case you didn't watch it, I will reiterate, but I do encourage you to go watch that one, at least the beginning of it. Its object's final velocity is equal to its initial velocity plus plus the velocity it gains from accelerating over a distance. An object's final velocity is equal to the initial velocity plus the velocity it gains over accelerating across a distance. Accelerating across the distance. What distance is this ball going to accelerate across? At least when it's falling, is going to be the vertical distance. So it will not be accelerating towards across this distance. At least not in this case. And if it was, it's unimportant because we're looking for how long it takes it to hit the ground. How long it takes it to hit the ground. So let's see. This will give us final velocity, which is not what we're looking for, but every every bit of information that you can get is very useful. So let's go ahead and start with that. Or, or if you note that the initial distance, if you note the initial distance as 0 meters, you could use this bottom one as well. You can also, yeah, you can use this bottom one as well. Um, or actually, it really doesn't matter. You could. There are two ways you can approach this with the bottom formula. You could see it as the distance it will travel. Uh, its its final distance, which is going to be 0 once it hits the ground, is going to be equal to the initial distance, which is 52.5 meters, plus this component, which is 0 meters per second times time, which doesn't really matter because 0 times anything is 0. So we can cancel this out. In this case, plus 1/2 is acceleration times time squared. And from here, you can solve for time. That is one way to approach it. The other way to approach it is seeing it this way. The distance it will travel is 52.5 meters, or negative 52.5 meters, because it will fall down this distance. And it initially starts at, we'll call this 0 meters. 0 meters plus, as I said, the initial velocity is 0 plus 1/2 at squared. You could use this formula. You can also use this formula to find some additional information. I do encourage you to find as much information as you can, as it may aid you um, in future steps of the problem. Um, so for the sake of this, I will go ahead and solve for v final squared. I mean, for the velocity final. So the initial, which is 0 squared, plus 2 times the acceleration, 9.8 per second squared, times its distance. The distance that it accelerates across is 52.5 meters. Is going to be equal to this velocity final squared. Um, yeah, velocity final squared. Okay, this I'm going to describe something that seems a little, I guess, not sure how to. Let me just describe it. Um, when we solve for this right here, we're going to get a negative value. And you can't square root a negative value because we need to square root both sides to get velocity final. You can't square root, well, you can, but you'll get an imaginary number, which we should not get in this case. So what we should do is make sure that this value is positive so we can square root it. And then after that, we will then apply a direction to the final velocity. The reason we do this is because, um, well, for this formula, we need to square root something. And that's something that we square root needs to be positive. So if this is negative, we need to make it positive. In the case of this problem, because it is falling, we will assume that, no, we know that the final velocity is going to be negative because it is falling. That's the negative indicates that that the velocity is downwards, not upwards. So we will go ahead and make this um, positive. Sometimes you'll run into this. You can also see it this way. The acceleration is in the same distance in which it is falling. So um, both of them are negative, which makes them positive. You can see it that way as well, if that helps you. But all in all, you need to make sure that this value is positive, and then you can apply a direction afterwards. So square roots of 1029 is equal to velocity final, which is equal to 32.08 meters per second. In this case, we should round to two significant figures, but I'll just keep as much information as I can get for right now. So velocity final is going to be 32.08 meters per second. Okay, now we've gotten the final velocity. We could use this formula to calculate time, which is pretty straightforward. 32.08 meters per second is equal to the initial velocity, which is 0, plus its acceleration, negative 9.8. Oh, this velocity is negative. Forget that. Meters per second squared times is the time that it takes squared. Times the time it takes. Manipulate 32.08 divided by 9.8. T is equal to 3.273 seconds. Boom, 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 boom. So the time it takes for it to hit the ground is going to be 3.273 seconds. Okay. The second part of the problem asks what must have been the initial horizontal component of the velocity in meters per second, indicate the direction with the sign. What must have been the initial horizontal component of the velocity? How do we do that? Okay, okay. So for this problem, we know that the horizontal velocity is going to be constant. Why? Because there's no external factors affecting the horizontal velocity. Unlike the vertical velocity where gravity was a factor, um, the horizontal velocity will be constant. And if the velocity is constant, we can use this formula. The distance the item travels and the time it takes for that item to travel. This looks a lot like velocity average. Because in this case, it is equivalent to that. It's, in this case, because the velocity is constant, it is equivalent to the average velocity. You can see that if you were to take a constant velocity right here, and you would take the average across these two times, which is this time, uh, this velocity, and then this velocity plus this velocity, if you take the average, which you would divide by 2, you will just get 2v over 2, and the average velocity will then be equal to v. So this shows that if the velocity is constant, this velocity is also equal to the average velocity. Velocity constant is equal to average velocity, and therefore you can use this formula. So let's see if we can solve using this formula. How long does it take it to hit the ground over here? Well, how long does it take the ball to hit the ground? It takes this time. We were able to calculate that earlier. And the distance it travels is 116.3 meters. So the distance it travels horizontally is 116.3 meters, and it takes this amount of time to travel that distance. Then we have all the information we need to calculate the average, the the horizontal velocity. This horizontal velocity is 35.53 meters per second. Okay, next part. This is the second to last part. What is the vertical component of the velocity in meters per second before the ball hits the ground? Okay, so if we draw the ball at the very end, right here, let me extend this a little bit. Let's draw its components. So the horizontal velocity is going to be, as we see here, 35.3. We know it's positive, so we'll just draw that. And then its vertical component, let's see. We calculated it up here earlier. Um, no, we calculated it up here earlier. So this is it. Yeah, this is it at the end. We calculated this by using this formula up here. We had the initial velocity, the acceleration, and the distance in which it will fall. That will allow us to calculate the final velocity, at least in the y direction. So its velocity final in the y direction is going to be equal to negative 32.08 meters per second. Last question, what is the velocity in meters per second before the ball? Before the ball, just what's the velocity in meters per second of the ball just before it hits the ground? They asked for the magnitude of the velocity as well as the direction or angle in this case. Okay, so let's go back to what I was doing before. If we draw the horizontal velocity and then the vertical velocity, which is like this, we can see that its velocity um, is like this. You can see that its velocity is like this. So it's going to be going towards the ground in this direction. So we should expect an angle in this quadrant. Okay, so how do we calculate the magnitude? If you recall the formula that I showed you at the very beginning of the video, you will know how to calculate the magnitude. Go ahead and write it down if you can remember. Otherwise, I'll write it down here. I mean, regardless, I'll write it down here. The magnitude of the velocity is going to be equal to square root of the horizontal component squared plus the vertical component squared. So the horizontal component, in this case, is going to be this value, and its vertical component is going to be this one. So we squared this one plus the square of this one, and we take the square root, and we're able to get the magnitude. The magnitude of the velocity is going to be equal to 47.87 meters per second. Now what about the angle? I also went over how to calculate this. Um, I also went over how to calculate this value earlier. As I stated before, it is likely that the professor will not require you to have to calculate it, but for this problem, you will need to know how to calculate it. You can't use a protractor in this case unless you have some way of drawing out this and this accurately that you can calculate the angle. But in this case, we do not. At least in this case, I will not. So let's go ahead and use the formula that I wrote down earlier. The inverse tangent of the opposite over hypotenuse, in this case, is going to be the vertical component, which is the opposite, and then the horizontal component is going to be equal to the angle. Now let's see. We plug this into our calculator. We get that the angle is equal to negative 42.08 degrees. Does this make sense? Well, negative 42.8 degrees will be here. This is 45. 42 will be right about here, very close to 45, which does look a lot like what we have here. If you need this value to be positive, you just add 360 degrees to it, and you'll end up in the same point. 360, add 360 to it, and you'll end up in the same point, but the value will be positive this time. The positive value will be 317.92 degrees. Okay. An arrow is shot from a height of 1.4 meters towards a cliff of height h. An arrow is shot 1.4 meters. We have an arrow. It is shot with a velocity of 32 meters per second at an angle of 60 degrees. At an angle of 60 degrees, it lands on the top edge of the cliff 3.6 seconds later. Arrow and t. I will say that this occurs at t equals 3.6 seconds. That's when this occurs. What is the height of the cliff in meters per second? Well, we'll probably have to find that information considering they didn't give it to us. Let's see what way we can find that information. Let's see. Okay, so the arrow strikes the cliff at the top. So in other words, at the time that the arrow strikes the cliff, the arrow is the Y position of the arrow is going to be at the top of the cliff. In other words, this Y position will tell us the height of the cliff. So if we're able to find the Y position of the arrow when it strikes the cliff, in other words, in 3.6 seconds, we'll be able to find the height of the cliff. So let's see. What information do we have? We have the information. Its initial velocity is going to be this. It's going to be 32 meters per second. We'll break this part into two components, Vx and Vy, with the angle being 60 degrees. How do we get Vy and Vx? I'll tell you now. This has to do with, you know it, trig. It has to do with trig again. Um, so, uh, if you don't know how to do this, if you don't know how to calculate the opposite side of a triangle, I again urge you to review your trig. Um, if you would need to find this information, you probably will. You definitely will. You'll definitely be using a lot of trig in physics, so do review your trig. With that said, I will go ahead and write the formula. Um, the opposite sine of theta is going to be equal to the opposite over hypotenuse, which in this case is going to be equal to Vy over the magnitude of the velocity, which is 32 meters per second. So, how do we isolate Vy? We'll just multiply both sides by 32, or its hypotenuse, and we'll get Vy. What about the horizontal component? The horizontal component has the same approach, except a um, different one of these. I don't know the mathematical name for it, but um, cosine of theta is equal to the the adjacent side, which is the side that's the closest to the angle, um, not the hypotenuse, the side that's closest to the angle, over the hypotenuse. It's going to be the adjacent side over the hypotenuse. This is going to be equal to, in this case, Vx over the hypotenuse, which is 32 meters per second. And as before, we'll just use some manipulation, some algebraic manipulation, and we'll get cosine of theta times 32 is equal to Vx. So now we have two formulas that we can use to calculate Vy and Vx. Theta, in this case, is going to be equal to 60 degrees. So the vertical component is going to be equal to 27.71 meters per second. And the horizontal component is going to be equal to 16 meters per second. Very cool. All right, so now we have that information. What other information do we have? We have that t is equal to 3.6 seconds. That's the time in which it strikes a cliff. And we also have the starting position, the initial y position of the arrow, which is going to be 1.4 meters. All right, so with that, let's go ahead and write our formulas. Velocity final squared is equal to velocity initial squared. Okay, let's go ahead and underline what information we have. Do we have the velocity final? No, we do not. We have the initial y velocity. We have the initial, oh, we do have the initial y acceleration, which is negative 9.8 meters per second squared. And then the distance that it travels. Do we have the distance that it travels? No, we do not. We have the initial velocity, we have the acceleration. We do have the time that it takes to travel. So we'll be able to calculate the final velocity in this case. We have its initial position, its initial y velocity, the time it takes, its acceleration, and the time it takes. So we're able to calculate the final position, the final vertical position of the arrow after a given amount of time using this formula. Um, we will go ahead and calculate the velocity final now that we have the information for it, because the because this information may be useful to us later. Velocity final. Um, initial velocity is going to be its initial y velocity is going to be 27.71 meters per second plus its acceleration negative 9.8 meters per second squared times the time it takes 3.6 seconds. This will give us the final velocity, and this final velocity represents the vertical component, the final y velocity at the time that it strikes the cliff, 3.6 seconds later. So this is going to be equal to 62.99. Oh, that is incorrect. Apologies. Final velocity is going to be equal to negative 7.57 meters per second. Now we have the final velocity. We can go ahead and underline that. Okay, so now we can also use this formula too, if we wish to. But we'll go ahead and use this one. Its initial distance, its final position in the y-axis is going to be equal to its initial distance in the y-axis, which is 1.4 meters, plus its initial y velocity, which is going to be 27.71 meters per second, plus 1 half negative 9.8 meters per second squared times time squared. Time is going to be 3.6 seconds squared. Apologies, I missed the part. Times the time, 3.6 seconds. There we go. So we can go ahead and calculate the final position, final y position with this information. The final y position is going to be equal to 37.65. That's not a 6. 652 meters. with this information, we can go ahead and um, we know that the arrow's final position is going to be equal to the height of the cliff because at the time that it strikes the cliff, um, it is in this position. We'll go ahead. This is our answer. What's the maximum height reached by the arrow along its trajectory? Okay. So, um, maximum height. So we have an object and it goes across this path because this is the path that it travels uh, uh, because gravity is changing its vertical component throughout time. And it looks a lot like this. It does have a maximum point, which is right there. So how do we get that? Okay, so we know when you throw an object in the air, if you were to throw an object in the air, the moment it would reach its peak, right? The moment it will reach its highest point is the same moment in which it can go no further upwards. In other words, its vertical velocity is going to be equal to zero when it's at its peak, which makes sense. If your vertical velocity at the very top was not equal to zero, say it was 2 or 3, if it was positive, you'll keep on going up, and gravity will keep on slowing down that, will keep on decreasing that velocity until it reaches zero. Once it reaches zero, you can't move upwards anymore, and you would have reached your maximum height. So we know that the vertical velocity at the very top is going to be equal to 0 meters per second. In other words, yeah. The vertical velocity at the very top is going to be equal to 0 meters per second. Its initial velocity in the y component, which we have somewhere up here. Where is it? Where is it? 27.71, 27.71 meters per second. It's going to be equal to its initial uh, velocity. Do we have the time in which it reaches its top? No, we don't. We don't have the time that it reaches its very peak. It is not going to be equal to 3.6 because it hits the cliff, and when it hits the cliff, it's already falling downwards, as we've calculated here. Its final velocity at 3.6 seconds is going to be negative, so it was already falling downwards, and that cannot have possibly been its maximum because when it's at its maximum, its final velocity is going to be zero in the vertical, um, in its in the vertical direction. Do we have any other information? We have the distance that it achieves. No, we do not. We do not have the distance in which it achieves. We do have the at its maximum. That's what we're looking for. We do have the initial distance, which is going to be 1.4 meters. 1.4 meters. So let's see. What can we? Oh, this is in the wrong position. What can we do with this information? What do? We draw formulas: velocity final squared, velocity initial squared, plus 2AD. Oh, we also have the acceleration, which is negative 9.8 meters per second squared. 9. Okay, velocity final, velocity initial squared. Uh, its velocity final is going to be equal to its velocity initial plus acceleration times time, and its final position is going to be equal to its initial position plus its initial velocity times time plus 1/2 acceleration times time squared. So which one of these formulas can we use? Let's start from the bottom. Do we have the distance it is very top? No. Do we have its initial distance? Yes. Do we have its initial velocity? Yes. Do we have the time? No. Do we have the acceleration? Yes. Acceleration, we have the initial velocity. We don't have the time. We have the final velocity. We have the final velocity. Yes, we do. Initial velocity, yes. Acceleration, yes. The distance it travels, no. Yeah, we don't have the distance in which it travels. So we can use this formula to find the time, which we can then use this formula to find the distance, or we can use this one to find the distance. I will warn you in this case, however, this value is more displacement. Is more displacement. And you can interpret this formula, at least in this case, is going to be its final velocity, which is 0, is going to be equal to its initial velocity plus the velocity that it gains over accelerating this distance. But in this case, because its final velocity is 0, we're interpreting it like this. The initial velocity, the final velocity, which is 0, is going to be equal to its initial velocity and uh, the velocity it loses from accelerating this distance. Because we were going up, and as we're traveling this distance, gravity is pulling every step of the way until it gets to the very top. It's still pulling down, but at this point, velocity final is going to be equal to 0. So we need to interpret it that way. This is the distance. The distance that it travels vertically is going to be the distance in which gravity is pulling down. That is not the total distance, however, because we start at this point. We start at this point above the ground. So this distance that we're going to acquire from here is going to be equal to this distance plus our initial distance. But if we use this formula, we will get this distance will yield this entire thing because it's already adding this one. Okay, so you can use either formula, but for this case, I will use this one because I like this one a little bit more. 0 squared is equal to 2.27.71 squared plus 2 times the acceleration, 9.8 squared, times the distance. Negative 27.71 squared divided by 2 times acceleration, negative 9.8 meters per second squared, is going to be equal to the displacement, 27. And if you do this, you'll get that the distance that it travels is negative 39.1757 meters. But what does that mean? In this case, does it make any sense? In this case, it does not, because the displacement that we're considering um, is going to be positive because it is displacement is always positive. So we will disregard the sign. In this case, it is unimportant. We'll go ahead and use that. Plus the distance that it started out. That started above, which is 1.4 meters. So its total distance is going to be equal to 39.175 plus 1.4. This is our D max. This is going to be our distance at the very top. All right, finally, what is the impact speed in meters per second just before hitting the cliff? So we'll go ahead and write down our formulas. The magnitude of velocity is going to be equal to the square root of velocity x squared plus velocity y squared. If you're wondering why I knew to use these formulas, is because the impact speed is going to be, because it's going like this, is going to be, it's not going to be Vx only or Vy only. It's going to be um, the vector that these produce, which is going to be V, which is going to, this is the magnitude of V. And the angle in this case is unimportant. They did not ask for it. They only asked for the speed. So let's see. Vx. We know Vx. Hmm. Doesn't seem we do. But can we get Vx? Vx in this case is going to be equal to the distance. Vx in this case is going to be constant, which is going to be equal to, um, because it is constant, is going to be calculable using the average velocity formula. As I've stated, as if it's constant velocity, the constant velocity is equal to the average velocity. So the distance it travels horizontally, not vertically. We wouldn't use the vertical one. We want to know how long its velocity in the horizontal. So we want to know how long, I mean, what distance it covers and what time it takes for it to cover that distance. That is the definition of speed. So the distance it covers is going to be, we do not know the distance it covers. Dx, we do not know. But we know Vx. What am I going on about? We have Vx. My apologies. Vx is right here. It's going to be 16 meters per second. We calculated that by getting the horizontal component of the initial velocity using its angle and its magnitude. So that's Vx. Vy would be this. Vy would be this. No, it would not, because the initial velocity, its initial horizontal component, it's not going to be, well, it may or may not be equal to its final component. We are looking for its final component because the y and the velocity in the y direction is not constant. The velocity in the y component is not constant because it is affected by gravity. And we calculated what the final velocity in the y component was. It is this. And if we calculate 16 squared plus, we get the velocity, the magnitude is going to be equal to 17.7 meters per second. That is questions 2 and 3. Hopefully I have helped you understand how to go through this problem. I do urge you to try to, because your problem is going to be different from my problem, go ahead and do your problem and see if you can follow the same steps. See if you can go through the same thinking process. Come back to this video if you are lost, if you don't know where to go next. But do try to develop the mind of a physics student. You'll need to learn how to break these problems into parts. And yes, it is very meticulous, but you need it. You absolutely need it to solve these problems. Well, I hope I've helped you. I hope that you've understood this video. If you, as I've said before, Please email me, not email me, please DM me questions or group me. And hit me up with any questions you may have over physics. Please, yeah, yeah, yeah. Do try your best before asking me, though. As yeah, thank you for watching, and I will see you next time, probably.